Hello everyone, welcome back to the course on Instrumentation and Process Control. Myself, Neethi Mehta, Assistant Professor at Chemical Engineering Department, LJIET Institute of Engineering and Technology. So, as we all know that we have already started with our new topic, which is response of first order system. So basically first order system deals with those systems whose input and output can be represented by first order differential equation, right? Or the relationship between whose input and output can be represented as first order differential equation. All such systems are termed as first order system. Now, we have seen various physical examples of first order system in our previous sessions, like mercury in glass thermometer, liquid level system, mixing system, interacting tank and non-interacting tank, or interacting systems and non-interacting systems, right? In this particular session, we will start with how first order system responds to sinusoidal waves or sinusoidal input, right? So suppose we are giving sinusoidal response to first order system, then what should be our aim behind doing this particular derivation? In this derivation, we are trying to determine how actually the first order system responses to sinusoidal input or to sinusoidal forcing functions, right? So for that, we are considering here that a thermometer is in equilibrium with a temperature bath at temperature Xs. Xs is our steady state equilibrium temperature. Now, at time t equals to 0, right? At time t equals to 0, the bath temperature begins to vary. That means now we are putting our liquid to the heating mantle. So the temperature of liquid will be starting to rise, right? So for that, X, that is the bath actual temperature, which is present temperature, is equals to X of S, which is already the steady state temperature, plus A sin omega t. So this equation is in the form of omega tau, right, or omega t. This represents the sinusoidal input, right. Now here X is temperature of bath, Xs is temperature of bath before you are providing that sinusoidal disturbance. Capital A is our amplitude variation in temperature and omega remains the radiant frequency. Now, we all know that X minus X of S, we are just shifting the terms, so it will become X minus X of S, and we all know this very well that this is nothing but change in value, and change in value can be represented in the form of deviation variable using the capital letter of that particular term. So instead of writing X minus X of S, we can write capital X, right? So it will be capital X equals to A sin omega t. Now taking Laplace of that, it will be instead of X, it will be X of S equals to A sin omega t. Laplace of A sin omega t will be A omega upon S square plus omega square. So this is how a first order input will behave for sinusoidal function. If you are providing input as a sinusoidal wave, then its expression will be in the form of this term, that is A omega upon S square plus omega square. Now our job is to simply put the value of Xs in our original transfer function of first order system. So what is the original transfer function of any first order system? it is nothing but ys upon xs equals to 1 upon tau s plus 1. So instead of writing x of s, we will substitute this value and it will be in the form of ys equals to a omega upon s square plus omega square into 1 by tau upon s plus 1 by tau, because we have simply taken tau common from this term. Now, we just need to take the inverse of Laplace of above equation, and once you take inverse, you will see that it is in the form of standard equation, which is P cos B plus Q sin B equals to R sin P plus theta, right? And where the value of R is under root of P square plus Q square and the value of theta is tan inverse P by Q. So simply substituting those values of identity, you will get the final derivation, that is y of t equals to a omega tau upon tau square omega square plus 1 e raised to t by tau plus a upon tau square omega square plus 1 sine into omega t plus 5, right? So this is how our final term for sinusoidal input look like. Now, what is the basic outcome of this particular derivation? So once we complete this derivation, we can understand how the output sine wave with a frequency omega equals to the input signal wave, right? So this is the most important thing which we learned from this particular derivation. And second thing is the ratio of output amplitude to input amplitude can be determined using this, and that ratio is always smaller than 1. And lastly, we can determine what is the transportation lag or what is the output lag. Lag refers to what time it takes for my system to give the output once you have given the input. That delay in giving the output is termed as output lag, and that can be determined using this sinusoidal response. Now, let's discuss about next input method, which is impulse input method. In case of impulse input method, what we can do is we simply need to put the value of x of s as 1, and now just substitute this value in our original transfer function, which is ys upon x of s equals to 1 upon tau s plus 1. So you will get the desired equation in the form of ys equals to 1 upon tau s plus 1. Taking tau common from numerator and denominator, you can obtain the equation in the form of ys equals to 1 by tau upon s plus 1 by tau. Now once you take its inverse, so it will be in the form of e raised to minus t by tau upon tau. So I have simply multiplied the tau here, so it will be tau yt equals to e raised to minus t by tau. So this is the desired output for impulse response system. Now, generalization of several non-interacting systems in series, right? How we can simply write generalized formula for non-interacting systems. Suppose we are having number of systems which are connected in series. So what we can do is we can simply write it in this form. Suppose this is x0 is input for first transfer function, x1 is output. This x1 serves to be input for the second block and x2 is output from the block number 2, and so on. So we just need to write the block equilibrium, that is output upon input equals to whatever the value is inside the block. So x1 by x0 equals to k1 upon tau 1 s plus 1. So here you can see that formula, x1 s upon x0 s, that is output by input, equals to whatever is written inside the block, which is k1 upon tau 1 s plus 1. So this is transfer function. In the same way, for block number 2, we can write x2 by x1, x2s by x1s equals to k2 upon tau 2s plus 1 and so on. So, if you need to write for nth number of terms, right, you need to write for nth block. So, it will be in the form of xns upon xn minus 1s equals to kn upon tau ns plus 1, because here you can see that whatever number is written here, the same number is written in this side also, right. So, this is generalized way. Now, if we want to obtain that overall transfer function, we can simply write it in the integrated form of this particular way, that is xns by x0s equals to summation I equals to 1 to n ki by tau is plus 1, and this is the graph which represents how the value changes or how the output changes for the given value of t by tau for n equals to 4, n equals to 3, n equals to 2, n equals to 1 and so on. So, once you combine the block, how its response changes, that can easily be seen from this particular graph, right. So, this is all about today's session. Hope whatever we have covered today, that is the different input method, that is sinusoidal input method and impulse input method, and also generalized way of writing the formula or transfer function is quite clear to everyone. Hope all the things which we are doing till now is quite clear. Thank you.